Okay, welcome to this second lecture in Open Quantum Systems. In the first lecture, we derived this equation that will be the starting point of today's lecture. Then let me remind you the general framework we have. Our main problem is that we have a quantum system that is very big, or some parts of it are not of interest to us. So this will be the total system. That the states of the system belong to this Hilbert space that we call total Hilbert space, and we have, of course, a total Hamiltonian that describes the dynamics of this total system. Thanks to Schrödinger equation, if you have a pure state, in a more general case, due to von Neumann equation, and of course, each state will be, in the general case, described by density matrices in the total system. But as I said, we are interested only in a small part of this total system, this part that we call our system of interest, and all the other parts that we are not interested on describing its dynamics, we call it the environment. To do so, we divide our total Hamiltonian in our system of interest Hamiltonian, our environment Hamiltonian, and then we have also an interaction between them two, because otherwise it would be just independent dynamics, and it doesn't. We wouldn't require all these techniques. And just a reminder, the total density matrix we can split in the density matrix of the system and the environment. In general, you cannot write it for a general density matrix. You don't write it like this. This is only for separable systems. If there is entanglement, you cannot do so. But in the previous lecture, we made this assumption that the system and the environment remain disentangled for all times. Just a reminder that the interaction Hamiltonian, we use this expression, that this is general. This doesn't require any assumption. Basically, you just split in the operator that acts on the system and the operator that acts on the environment. That this is something that we are going to use right now. And reminding that we are working in the interaction picture. And if you have seen the previous video, I also have to remind that I always forget to write these hats, okay? But at this time, I will try to be careful, because eventually we have to come back to the Schrödinger picture. So I will have to remove the hats. So there will be a moment where there will be some operators with hats and some operators without hats, and it's going to be a little messy, okay? So let's try to keep it consistent. And I will also check my notes several times, because I want to keep the notation I have here, because you are going to see that now many indexes will appear, K, L, omega, omega prime, epsilon, epsilon prime, and I want just to be consistent, so if in the middle I understand or we don't understand something, I can check, okay? So as I say, we are going to start from this equation. This is what is called Redfield equation. In the previous lecture, we went a little further, but here we are going to start from here. This is an equation that is already Markovian. We have used the Markovian approximation. This is why this integration goes to infinity, because we assume that this decays, there is a correlation factor that decays very fast when you integrate over time. And it is already Markovian, but it is not positive and not completely positive, meaning that the density matrix that you have here, that is described by this evolution, it doesn't need to sometimes with the time evolution, you obtain a matrix that has some negative eigenvalues, okay? There is one further approximation we need to do to make it positive. And this is the one that we will do today, and we will arrive to the Lindblad master equation that is a completely positive and trace preserving master equation, okay? So first of all, what we are going to do is to yellow. I'm going to write all the steps so we see what we are doing. Now we are going to deal with many expansions and many terms of this equation, because we are going to expand this commutator, and only at the end we will be able to take everything back to a commutator. Okay, so first of all, let's expand it. So let's see if we can work with it. This is hat, okay, this will be alpha squared. Let's take different integrations, okay, differential of s, 0. Let's just expand this commutators. Okay, so it will be hi of t hat hi of t minus s hat rho t of t. This will be one term. Then between 0 and infinity, differential of s. We take this commutator, so it will be hi of t rho t of t hi of t minus s hat. Oh yes, sorry, thank you. The trace over e, we keep it here, okay? So we trace over all the terms. Then there will be another term, sorry, this will be this commutator multiplied by this. Okay, now we take this to the other side. It will be hi t minus s rho t of t hi of t minus plus the last term that will be between 0 and infinity of rho t of t it will be how is this rho t of t hi of t minus s. Okay. Sorry.
Yes.
No. It will be t minus s minus. Sorry. And then at the end will be this rho t minus st. Yes. This is hi of t. Hat. Yes, definitely this one. Okay, and now we are going to expand this first on this basis, and then we will play a little bit with it. But to do so, one thing that is helpful is to notice that this second part, this is the Hermitian conjugate of this first part. Okay, if you make the Hermitian conjugate, you just apply the rule. Here all matrices are Hermitian. Okay, so it just you have the trace of ABC. You have ABC. You take the Hermitian conjugate. You get CBA. Okay, so this will be equivalent to this, and this will be equivalent to this, and then we can work only with half the equation, and then we will write all the time plus a Hermitian conjugate, and we just save some of the calculations. Okay. So now, before we unravel all this equation, we are going to change, or we expand in the system eigenbasis. So imagine that we have our system Hamiltonian. Of course, this is a Hermitian matrix. We can diagonalize it the following form. So we will get a set of epsilons that fulfill this, and we know that these epsilons correspond to the energy of the system, or the eigenvalues of the energy of the system. Okay. Now what we are going to define is some operators, is I of omega, or yes, I of s I hat is the same. Okay. This is psi omega, let's write the hat, okay? Let me see if we write. No, Si, sorry. It's just an expansion of our projection this way. I prime is I epsilon. Let me see if prime of no prime. As I said, I want to keep notation consistent, so the other way around. Prime and prime. Okay? Where this omega is just a difference between energies. So I fix the difference between energy, and then I sum over all E and E prime such that omega is equal to E prime minus I. Let me see again if it is E prime minus I, or E minus E prime? Epsilon, oh. Okay, correct. Okay, this is just a definition. I take all the eigenvalues of the energy, I define all the possible differences between these eigenvalues, and I define this projector. One thing that you can see is that SI is just the sum over omega, the SI omega. That is the function we are going to do now. Yeah, think a little bit about it. Simple, isn't it? Because if I have this, if I fix the omega, I just sum over all epsilon, epsilon prime that fits with this omega. If I then sum over all the omegas, I'm summing here over all possible epsilons. Okay? And this will be the identity. And I'm summing also over all possible epsilon primes. And this will be also the identity. Okay? And I recover SI prime. Cool. If this is clear, then we can apply to this equation. But the difference is that in this equation we have HI hat. Okay? And this I have defined for SI. This was checking before. So let's try to relate SI hat with respect to this SI omegas. Okay? SI will it fit down? Just trying to save a lot of space. Okay, let's do it here. It won't fit. If we are in the interaction picture, this SI hat, I copy it here. Okay, transformed by this definition. This is exponential of I H plus H environment T SI. Exponential of minus I H plus H E of T. Okay? And if we want to expand it this way, we just this is equal to exponential of I H plus H E T summation of A omega, this I of omega, and the exponential of minus I H plus H E of T. Cool? Then I take the summation out, so it will be A plus H E T is I omega, exponential of minus I H plus H E T. Okay, so there are two terms. One we have to work a little bit, the other one we don't. The first one that we have to work, the one that we don't need to work is regarding this environment Hamiltonian. Because this is an operator acting on the system Hilbert space. This is an operator acting on the environment Hilbert space. So they commute. Okay? And as they commute, this part will cancel with this other part. Now to use this here, it makes sense, no? If this is a positive exponential, this is a negative exponential, it makes sense that we try to do the same. We commute it and we see if they cancel. But to see if we can commute it, we need to know what are the commutation rules between H and SI of omega. Okay? These commutation rules will be very useful. Let's calculate them here. And let's try to keep this for the rest of the lecture. Okay? So basically, I want to know what is H SI of omega. If I know this, then I can apply this, commute this, and see if H and minus H, they cancel. Basically, how do we do this? This will be S SI of omega minus SI of omega H. And this will be equal to H. Let's use the definition. Epsilon prime from omega fixed of epsilon prime SI, no sorry, epsilon prime epsilon prime minus sum epsilon. Okay, this will be one term. The other term will be epsilon prime omega, or epsilon si epsilon prime and Hamiltonian. It's just applying this. The definition, we plug it in here. And now with this H, we use the fact that this epsilon or this epsilon prime are the eigenstates of the Hamiltonian. So this will be basically epsilon, okay? We take this epsilon from here. Let's make the summation. Summation over epsilon is I epsilon prime minus the summation, this acts to epsilon prime, so epsilon prime and the same. Epsilon is I epsilon prime. And you see that I can take epsilon and epsilon prime as common factor because this and this are the same. Okay, so this will be a lacking space. Let's take it here and then I copy just the commutation relations. This will be the summation of epsilon minus epsilon prime of epsilon si epsilon prime. And we are summing over epsilon and epsilon prime such that omega is equal to epsilon prime minus epsilon. Okay? So, principle, we are summing over epsilon and epsilon prime, but luckily we get here, we don't get epsilon and epsilon prime independently. We get the difference but this rule, we are keeping it constant because this, okay, broke my first shock. This is the same as minus omega. So this will be just minus omega, and this I can take out, okay, because the omega is the same for all epsilon prime I get. It will be just minus omega si of omega. Clear? Okay. Just a little algebra. As I say in the other lecture, these are the typical things that in books are saying very easily you get to, and it's true that it's very easy, okay, but requires a little calculation, okay? So let me erase this because this we are not going to need it. But we will calculate something similar close to the end. But here let's write just the solution. This minus omega is omega. Now let me write it explicitly because at least to me it's very helpful to make calculations. Okay, because then to me when we find something like this, to me it's easier to move things around and not get confused with the sign. We are also going to need this other condition. So what happens instead of the system operator, I have the adjoint, the complex adjoint of the system operator. Okay, the complex conjugate, sorry, of the adjoint. And this you can calculate yourself. Basically the same operation, it gets just a sign. Okay, let me also write it explicitly. Omega minus si omega dagger h is equal to omega si of omega. And now we come here. Here, let's move things in this direction. Okay, let's try. What I want, just to give you a hint of the idea, is this. If I move here, I could do the other way around, of course. Okay, but if I move this here, maybe if we are lucky, this Hamiltonian will cancel with this Hamiltonian. and it will. This is why we do it, okay? What do we have here? HS, that will be HS, okay? Basically, what we can say from this rule is that exponential of A H T SI of omega is equal to the exponential of minus omega T I. This comes with a plus H I H T, and I got very excited with the exponential. I forgot the SI of omega exponential. I said this minus omega T I plus IHT. Okay, this comes directly from this commutation relation. This we can plug here, and what we get is that this is equal to the sum over I of the exponential of minus I y t SI of omega. As this is in the right, but this is just a number. As it is a number, I can just take it back. Okay? It doesn't matter if I write it here or if I write it here. Okay? So this trick, what allows us is to change back. Okay? This, remember this, they don't have a hat anymore. This is why now it's important to write the hats explicitly and don't forget them, because we are explicitly changing back to the Schrödinger picture only for these operators, and you get the time dependency in a very nice way that you can work. Okay? And now is when we get to the funniest part today, because it's making lots of calculations. Okay. Let me check the indexes. Okay. Basically, we have this. Okay, this definition here, and this we are going to apply to this expansion that we did here. Okay, let me see, because maybe the expansion I have it here is but here, let's say that I use the same term, t time minus s 1. This one, the one we are going to use. Okay, we are going to expand it. Okay, we are going to expand. Of course, as I said, these were the complex conjugate, but it's also true in this way, that this is the Hermitian conjugate, of these two. Because this is just one by one. This is the Hermitian conjugate of this, and this is the Hermitian conjugate of this. Okay, so we are going to calculate, not for any special reason, but this because it's what I did before, these two. We calculate these two, whatever we get, the complex conjugate will be the other one. Okay? And to do so, we are going to expand the S parameters that are hidden here and that hidden here. Okay? And we are going to use the fact that the interaction Hamiltonian can be written in this way. Okay? But we are also, let me write it here. So we have everything compact here. It's true that this is the sum of SI times EI. Okay? Hat and hat and hat. Okay? Sum over I. But it is also true that this is the sum over I of SI dagger times EI dagger. Why? Because the Hamiltonian is Hermitian, so if I take the complex conjugate, this should be the same. Okay? We are going to do so because we want to have couples of operators and complex conjugates of the operator, or adjoints of the operator. Okay? It's one choice. And basically, we are going to start with this one, let's say, term 1. See if I can copy it. Will be, I forget the alpha square, I will add later on. Will be the integration between 0 and infinity of hi of t minus s, if I don't think wrong. No, hi of t, sorry. T, hi of t minus s, rho total that I'm going to expand as rho of the system times rho of the environment. Principle, both of them can be time dependent. This we saw in the previous lecture, that at this point they can depend. The state of the environment can depend on time. You will just get something more complicated. And there is a normal assumption to assume that the environment doesn't change with the time. So it's very big, the correlation very fast decaying, so you don't need to take care of it. But we will make this assumption just at the very end when we are forced to. And now let's expand this. The only thing is that, as I say, we can use this expansion or we can use this expansion, whatever we want. Okay? So let's use 1 and 1. If it is t, we are going to expand in the set of, in the adjoint. So we are going to use this expansion, and this is the index that we name. You say that here we use I. We are not going to use I any longer because it can get confused with the complex variable. Okay, so to the imaginary number. And this one we are going to expand as SL. Okay, of course, of omega. This I didn't say. We will have 1 omega for this expansion, another omega for this expansion. So the first omega is, this will be SK of omega prime, and this we will call SL of omega. Okay, just a choice of the names we give to this dump variable that we have. Okay, it doesn't have any special meaning. And of course, you could use here the normal and here the adjoint, just to be consistent. Clear? So what comes from here, HI, we expand as say like this. Okay, so we will have summation that comes out of the trace, of course, over K. Let's do it explicitly so we don't skip one step. Okay, we get the trace over E, we get the integration, infinite. Here I forgot the differential of S. Okay. This will be the sum over K and over omega of SK omega, because I have to sum first all the operators, and for each operator I have it, no, it's here. Okay, no, here. Okay, each operator I add over omegas. Omega prime. Okay, it's omega prime times EK EK of t, and now what is missing is the time factor of this SK. That it will be, as we are working with the adjoint, it will be times exponential of I omega prime. Okay, because it's the complex conjugate. Sorry? EK Dagger, yes. This multiplied by the sum now with L and omega of SL omega times EL hat of t. And now I separate the factor, the time dependency, so we can be careful. It will depend on omega. It will be exponential of minus I omega t minus s. Okay? Omega, because we are expanding in omega, t minus s, because here is t minus s. And this, of course, should be also t minus s. If it is correct, I didn't make any mistake, this is what we get. Okay? What can we do now? Eventually what we want is to trace over it and to separate the system part from the environment part. And this is why we make this separation. Okay? So let's take the summation out. K, L, omega, omega prime. Integration between 0 and infinity of, let's now separate the part that belongs. Okay, I forgot, you didn't tell me, the density matrices. Sorry, it should be here. Otherwise, this doesn't make sense because these are the operators. So system of T times rho environment of T. So now we separate the system and the environment, because by this rule we can apply this and this to the system and the environment to the environment. Okay? So this will be something like Sk dagger of omega prime Sl omega exponential of I omega prime minus omega T rho S of T. Okay, so this will be the system part. Then we have this S here times exponential of I omega S, and now the trace will act only on the environment part. That will be trace over Ek dagger of T El T minus S hat rho E of T. Differential of S. Always integrating in S. Okay, I think I didn't forget anything. And luckily, all this part, all this up to here, this does not depend on the S, that is the variable that we are integrating. So everything there can get out of the integration. So we will get the sum over K L omega prime of Sk dagger of omega prime Sl of omega exponential of I omega prime minus omega T rho of T. I'm writing here of S, but I say at the beginning that the system has not subindex, okay? And this will be one parameter. I just make all this integration, KL of omega. Where KL of omega, now something very gamma KL of omega, sorry. Something important from now on is just this integration between 0 and infinity, differential of S, exponential of S, I omega S, of the trace of Ek of T, El is correct, is K first, yes, of T minus S, rho of T, and this rho of the environment. So, if you see, now what we have done is to separate the system dynamics, that is this part here, okay, from the environment dynamics, and the environment dynamics is just this integration, that in principle, and this is where I say, I said before, that up to this point, we haven't assumed that the environment is stationary, that the environment doesn't change. It could change.
The epsilon k should have dagger, isn't it, in the trace?
Yes, yes, yes. The first one. This is dagger. Okay? And these are basically, if you remind the previous lecture, this correlation function that we assume that they decay very fast, and this is why we can take this integration until infinity instead of between 0 and t. That will be non-Markovian. So here is the Markovian approximation, but also if we assume that the state of the environment is not a function of the time, okay, then you have here something that depends only in S, that is the variable that you are integrating, okay, and then you have that these factors are constant with time. That is the usual approximation that we use in the Limblad master equation, okay. So then we will have a phenomenological master equation. This, that is what comes from the environment, you integrate, you calculate it one, and then you have an equation that only deals with the system state, okay? So this will be the seed of the Limblad master equation after we massage it a little bit. So we have this, the first term. I say that we can calculate both, but I think the other one is just exactly the same. Okay? Is you make the expansion here, you just change the order of the Hamiltonians, and then you work it out a little bit. So I don't think it is really necessary to go through it. So let's take this space and write what comes out of it. So basically, the equation we get after working with all of them looks like something like this. So hat t dot is equal to alpha square exponential of I omega minus omega prime, I think. No, omega prime minus omega t gamma of k L of omega, the commutator of SL of omega, SK omega prime, no, SL of omega rho T, SK dagger of omega prime, plus the Hermitian conjugate, that is exponential of minus I omega prime minus omega T gamma conjugate of LK omega of omega prime in this case, and then SK of omega rho of T SL of omega prime, and one of them should be dagger, and this one, okay? This comes from combining 1 and 2, 1 and 3, no? Let's say 1 and 2, sorry. And this is just the Hermitian conjugate. Basically, these commutators comes, because if you see here, you get SKSL rho. This exponential you can move out. In the other case, you will get SL rho SK in the other case, okay? If you have followed this explanation, doing this is quite simple. It doesn't, I think, it doesn't pay off to make it here explicit. So this is the equation we get. You can see that up to now, it's only math, okay? It's only just calculation with no physical assumptions, also not very calculated math calculations. The only thing is just to work with the commutators and so on. But we haven't, the only assumption we have made, and we don't need to make, okay, we can keep it out, is that this, the state of the system, the state of the environment, sorry, doesn't change with time, so these gammas are not time dependent. But if we don't make this assumption, we just write here omega gamma, omega t, sorry, and then we can keep our calculations until the end, okay? So it's not a required assumption. Now is where we are going to do the assumption, the physical assumption that is basic for the Lindblad-Master equation. This one, this equation is still totally equivalent to the Redfield equation we started with, because we haven't made any other assumption. Okay, so this is equivalent to this. And we say that this is not completely positive. We are going to make one more assumption that makes it completely positive. This is called the rotating wave approximation. Also, in some books, called secular approximation, but this is not exactly the same. Not for all the systems, secular approximation and rotating wave approximation is the same. For one qubit, for instance, it is the same. For a general system, it is not the same. And the one that we are using here is the rotating wave approximation. Okay, and this basically is this approximation. Okay, here I have forgotten, of course, the summation. Okay, this sums over k, L, omega, and omega prime. Okay, this comes here because we make this expansion, so we have to sum over all possible omega and omega prime. That comes from the eigenvalues of the Hamiltonian, of the eigenenergies of the system. This that depends on the environment, and this that comes from the interaction Hamiltonian. So we have to add all of them to get our dynamics. Basically, the omega and omega prime, that are energy differences, they appear only in these terms here, these exponentials. And these are complex exponentials. So you know that complex exponentials, they mean that you have oscillation. You can expand just the sine plus the I the cosine, and then you have rotation. Okay? So basically, the rotating wave approximation, what says is that if these frequencies, or this frequency difference, is very big compared with the typical dynamics of the system, okay, compared with the absolute values of the epsilon, you will have something. Basically, you can split your dynamics, or the dynamics of this part, that can be whatever you want, something like this, plus the dynamic of this part, that will be very fast oscillation. It will be very fast if this is very big. Okay, if this is a very big term, then you oscillate very fast. Okay, and if you oscillate very fast, what happens is that this part will go down and up and down and up and up and down. So if the typical dynamics of your system is very slow compared with this frequency here, most of the expansion, most of this term of this summation on omega and omega prime will cancel out, because they go positive and negative, positive and negative, positive and negative. Okay? The ones that will survive are the ones that have this very, very small, in the limited case, the one that this is 0. So because when this is 0, you have omega equal to omega prime. Okay? This, you can perfectly forget about this term. This will be just the other dynamics who rules, and this will be the only one that doesn't cancel when there are fast oscillations. Okay? And this is the rotating wave approximation that allow us to make omega equal to omega prime and cancel one of these signage. Okay? And this trick, removing this, is what makes this equation positive, or completely positive. So basically, after the rotating wave approximation, we get something that is very similar. This rho dot of t equal to alpha squared summation over k, L, and omega of gamma k, L of omega SL of omega rho t sk dagger of omega. Let's write in just one line, plus gamma lk star of omega prime sk of omega rho of t sl dagger of omega prime.
Then omega equals omega prime, so we should...
Yes, sorry. Prime. Okay, and we have removed omega prime, and we forget about omega prime for the rest of our lives, basically. Okay, so this is our equation. Basically, again, we are going to massage it a little bit, but as this was equivalent to the Redfield equation, this is already equivalent to the Lindblad-Master equation, mathematically equivalent. We will see that now we make mathematical transformation to just give it a form that we can play with, that is interesting, and so on. Because this one is something that it's very hard to work with. Okay, it has summation, you have to calculate many of these gammas. We are in the Heisenberg picture, that is not easy to work with. Okay, so we are going to do basically two things now. Well, three things, but the first two were, one is in physics, in quantum physics, we are very fond of Hermitian operators. So let's try to transform this gamma, that these are numbers, but you can order them to be a matrix. But this matrix, this gamma, is not Hermitian, it doesn't fulfill anything. Okay? It depends on the correlators, that when you change them are Hermitian, but you are also integrating over I omega s, or I minus omega s. And this makes this integration is clearly not necessarily the complex conjugate of the other one. Okay? But this gamma, KL, omega, they are not necessarily Hermitian. So let's just transform them in two parts. One that is Hermitian, the other one that is not. Let's try to extract as much Hermiticity as we can. And when we do that, we will just move back to the Schrödinger picture. That will be the almost last part, okay? So to move them, to move to the to transform this gamma, this gamma matrix in a Hermitian operator, let's do this transformation. This gamma k of omega, we are going to transform into 1/2, half of gamma kl plus I pi. This will be, if this depends on omega, this depends on omega 2 plus pi kl or lk kl. Okay. This is where I say we have to be very careful with don't switch in KL.
Can I ask a question?
Yes, ask.
Do we lose anything with that last approximation, like physically? Because I'm trying to understand, because you mentioned something in the sense of every, in the sense of
the rotating wave approximation, if it means something physical. Yes, physically you can see this is just extra. Just a small explanation, okay? Imagine that you have one two-level system. That is the easiest way. Okay, here you have only one omega for the system. That is the difference between these two, okay? Imagine that in your bath you have many different frequencies, okay? Imagine that you have a bosonic bath, for instance. Many bosons, each of them can have a different energy splitting, okay? The ones that have an energy splitting, epsilon prime, that is different to this. Okay, sorry, let's keep the notation. This will be omega. This will be equivalent of omega prime. Okay, you have many of them. This is why you have to sum. In this case, you sum over all the omegas of the bath. Okay, the ones that do not match this omega will make just try to make a very fast motion between the atoms, while the dynamic of the atoms is given by this omega. This is much slower. So it will be that these omega primes, they will, if the atoms behave like this, they will make just very switch of oscillation of this that goes positive and negative, positive and negative. It make just, or if you forget about the positive or negative, if you just, because here we are plotting something that is unphysical. If this is the system dynamics, basically, if this is some operator or something, it will make oscillations that are very fast compared with the system dynamics. So they cannot, say, physically couple to the dynamics of the qubit. And this is the only the harmonic oscillators that have a similar frequency of this is the one that will resonate with the 2-qubit system and can alter the dynamics of the system in the long term. Okay? So this is basically the basis of the rotating wave approximation. This is why it is used not only for the Limblad master equation, but in quantum optics it is very widely used.
Could I say, for example, that this approximation would be somehow equivalent of saying that the energy levels are quantized in the same, like separated in the same like degrees of levels, because they're making exactly the omegas equal to omega prime for every omega prime. Like it's like approximating the actual spectrum of the energy to a spectrum in which every difference between levels are the same.
Yes, it would be something like that. I would have to think about it, but basically it's only taking into account the splitting energies that are the same as the splitting energies in your system, basically. Yes?
So this approximation is also what gives us complete positivity, correct?
Yes.
Is that obvious to see immediately?
If it is easy to see, no. Maybe in a future lecture,
okay.
by Mihalis, he will prove that this is completely positive, but it's totally non-intuitive and it's not just one line of calculation that I can do. Okay, you have to when you end up with the Limblad master equation, that is, as I say, it's hidden here. You can prove that it is completely positive, but you need other tools that we are not talking about, like the Choi-Yamir-Kolsky isomorphisms. Okay, so I cannot prove it in this lecture.
And there is no intuition as to why.
It's not easy to me to give. It's more, I know the mathematical proof, but they cannot give any intuition. Okay? Yes?
If someone is measuring our system, can we describe it with this? Or that would be...
Yes, the linear matter equation can describe you have a system and you have measuring the system. This we discuss when we have the equation. Okay?
Like, don't trace the certain maps. Yeah.
Okay. So where was I? Okay, I was saying that we want this gamma to transform into Hermitian matrices. Okay, because we know how to work with Hermitian matrices basically. So we are going to do this. We have two. We have the gamma KL, the gamma LK. Yeah, no, it's basically the same. I'm missing something because here. Okay. Otherwise, I couldn't take the complex conjugate. Okay. And these are Hermitian matrices. These are described very easily. Gamma KL of omega will be gamma KL minus or plus gamma LK complex conjugate of omega. Pi KL of omega will be equal to minus I half gamma KL of omega minus gamma LK star of omega, complex conjugate. Okay? This is quite easy. You just complex conjugate this, you get here a minus sign, and then you get a set of equations, two variables, very easy to solve, and then you get to this. Okay? And from here, if you get to this, you can see that both of them are Hermitian. Both gamma and pi are Hermitian matrices. Okay? We are, as I say, this non-Hermitian, I cannot decompose into Hermitian matrices. This is why I need to have a plus I here. So this matrix is Hermitian, this matrix is Hermitian, but this term will be non-Hermitian and this term will be Hermitian. Okay? Because if I take the complex conjugate, this should change to minus I. Okay? So, more calculations. Okay? Let's continue here. Very funny ones. Rho hat dot of t will be equal to alpha square sum over k L of omega, and now I plug this 1/2 gamma k L omega plus I pi k L omega, and now the commutator SL of omega rho hat of t Sk of omega. Here, plus 1/2 gamma Lk of omega minus I pi Lk of omega. The second commutator that is here is Sk of omega rho t Sl dagger of omega. Okay, very nice expression. The only thing we need to do if we want to work it is to expand again this commutator that we had before, to expand this commutator, and then take the gammas, take the common factor. We are going to order all the terms that go with gamma, all the terms will go with pi in the other side. Okay? And this, let me please copy it, because otherwise we won't finish ever. So this will be basically the summation alpha square, the alpha square. I'm keeping it all the time, but we can just absorb it in the gammas, okay? So at the end we don't need any alpha square because it's just a factor. So we just rescale all the gammas by alpha squared, and we forget about it again forever. L and omega will be just gamma KL of omega. Let me copy it, say SL of omega rho hat of T Sk of omega minus 1/2 Sk dagger of omega Sl of omega rho of T minus 1/2 rho of T Sk dagger of omega Sl of omega. And I'm missing one bracket here. Minus I pi of KL of omega S K dagger of omega Sl of omega rho hat of T. As I say, just a little massaging of this. You expand this, take the gammas, you take all that goes with gamma, all that goes with pi, and then you just recognize that this term is a commutator and you commutate it. Okay? If you have ever seen the Lindblad master equation, ever? Yeah?
I think you miss a dagger in the first square parenthesis.
Yes, yes. If this is S dagger S, this should be S dagger.
Yeah, in the first line, also in the commutator, the S up.
Okay.
A little bit up.
Okay, yes. It was. Then let me check so I read it correct. I can take it. No, it's LA.
It should be.
This comes from here. Yes, SL omega SK dagger. Okay? Thank you. Okay? So if you are used to even if you are not used to the Lindblad master equation, here you can identify two parts. Okay? For sure. There is this part. Okay? And this other part that is different. Okay? Here we have a matrix. Cool. And we have this term that if you know about the Lindblad master equation, you would recognize that this is the dissipative part. But even if you don't know of the master equation, this should remind you of something. Okay? This term, as you know a little bit about quantum mechanics, what does it look like? It is basically the von Neumann equation. If we assume that this is like a Hamiltonian, that let's call for some reason HLS, this is just the von Neumann equation. Okay? For some reason, of course, there is a reason. Okay? This is what is called the lamp shift Hamiltonian. Okay? Lamp, we got a guy called lamp. Okay? No, it's not with the silence of the lamps or something like that. Okay? Shift, because we will see that this Hamiltonian now it will add to the system Hamiltonian. Okay? And what is usually interpreted is that what it does is just to switch, to move a little bit the eigenvalues of the system Hamiltonian. But this, I'm not so sure. Okay? So they say that it doesn't play any role in the dynamics. This is a common assumption that you can just ignore it. Some people say, okay, just for each system, prove me that you can ignore it. In any case, for the purpose of this talk, it doesn't really matter. You will see that we just not add it to our Hamiltonian, and we have a different Hamiltonian that we have to simulate. But the complexity of the system doesn't increase. The size of the system will be the same. I will just have to change my Hamiltonian by another Hamiltonian. Okay? So, wonderful. We have our equation. Basically, this is the equation. This, again, I have said several times, this is the Lindblad master equation. But it's not the Lindblad master equation we are used to see in books. Why? Because usually, when you work with these kind of things, you don't work in the Heisenberg picture. We have used the Heisenberg picture as a tool Also not to carry the Hamiltonian all the time, the interaction Hamiltonian, just to make this expansion, to calculate this exponential of omega t. All this came from the Heisenberg picture, from the interaction picture, sorry. But if we want to work with this, working in the interaction picture, sorry, is very painful. So what makes sense is to come back to the Schrödinger picture, and this is the almost last step. Where can I erase? Okay, I think this, no, this we are going to use again now. Okay, so this I don't erase. We need for these lectures bigger blackboard, okay? Or several of them that go up and down, and circular ones, so we have to get careful, okay? Okay, let me erase this if we are not going to use it anymore. We have now this wonderful thing, okay? That we want to go back. If you see, step by step, we have been removing the interaction Hamiltonian, the interaction picture, sorry. Why? Because the interaction picture regarding the environment operators, they are hidden in these two matrices, okay? And this we don't care. We calculate it in any picture we want, and then we forget about them. And the one from the system operators of the interaction Hamiltonian, we have unraveled it by the use of this omega. And we put in this exponential, and to the rotating wave approximation, we got rid of this exponential. The only thing that remains in the interaction Hamiltonian is our density matrix. So we have basically to undo, okay, let's say. Next step is go back to Schrödinger piece. And you will see that it's quite simple. Basically, by the definition, this rho hat that we have and we want to get rid of it is basically the exponential we say before is here you use a plus I h plus h e t rho t exponential of minus I h plus h e of t. This is what we have to plug in here to unravel it. Okay, so it's just substituting. Here we have two terms, let's say, equality. So we have to substitute here in the derivative and here in the expression. So first in the derivative, that is the most interesting part. Derivative of t. This will be the derivative with time of exponential of I h plus h e. Well, before let's simplify our lives so we don't carry this all forever. We have also removed the environment density matrix with this assumption that it is separable, it doesn't create entanglement. We have removed it. So this is an operator in the system Hilbert space. Of course, it commutes with the Hamiltonian of the environment, or with the Hamiltonian part of the environment. For sure, this will commute here, and this part we can forget about it. This, we used it before already. Okay, so it's not to write he all the time and then cancel it. So we cancel it on the first beginning, and this is much simpler. This is rho of t, exponential of minus I h of t, h times t. Sorry. Okay. This is the left-hand side of the equation. How do we take derivatives here? We have three terms, so it's the derivative of this, times the other two, the derivative of this, times the other two, the derivative of this. Okay? So this will be IH rho of t, sorry, no, IH, the exponential of IH t, rho of t, exponential of minus I h t. So the derivative of this guy here plus exponential of I h t rho dot of t exponential of minus I h t. Okay, the derivative of this lady here. Okay, minus I yeah, minus I. We keep this exponential IT. No, IH, sorry. Let's keep this minus exponential of IHT, rho of t, IH, exponential of IHT. Okay? One thing that we know is that the exponential of the Hamiltonian commutes with the Hamiltonian, of course, because they are the same matter, okay? Basically. So we can write this in this way, exponential of IHT. And look, then here I'm going to have H rho, okay? And here you're going to have minus rho H, okay? This looks a lot like a commutator, okay? Commutator of H rho of t plus rho of t exponential of I minus. Here I forgot the minus, sorry. Minus, okay?
There's another piece.
There is what?
Yeah.
There is a, yes, there is an I here. Multiplied by this commutator. Otherwise, it wouldn't make sense because now you see that we have recovered, of course, the von Neumann equation. Okay? That is what you have to recover because the von Neumann equation is what gives you the time evolution of your system. So this is the left-hand side. To do the right-hand side, and also the right-hand side includes, remember, this coherent term and this other term. Okay? We need only one property, and we don't. I was thinking if we do it or not, but I think it will take me, if we make all the calculations, like 20 minutes, something like that. And it's very simple. Also, the idea is very simple, so we won't make it. The only thing you need to know to calculate the right-hand side is that if you go from here, okay, you just calculate this, between the Hamiltonian and S. Where are my notes? SI omega, SL, SK of omega, this will be equal to 0. Not very difficult to see, not very counterintuitive, because if you commute with S, you get a minus omega. You commute with S dagger, you get a plus omega. When you make it twice, this plus omega will cancel with this minus omega, and then you will cancel. Okay? And why do you need this? Because here, you see in this part, all operators come by pairs. Meaning that when you plug here, the exponential here, the exponential of minus ht, and here the exponential of ht, you will be able to commute in one direction, in another direction, here very easily because you have two and they commute. Okay, here you just commute twice, you get a plus omega and a minus omega, and you cancel. Here you just directly commute, okay? And at the end, what you will get is the same as here, but with here an exponential of I ht, and here an exponential of minus I ht, okay? So it's the only thing that will happen, because all the operators, they come by pairs. Here it doesn't happen, okay? Because here we don't have these S operators. Correct? And then you can just equal this to this here, and you cancel this exponential with this exponential, this other exponential with this other exponential. So the only thing that really matters when you change to the Schrödinger picture is that you get the von Neumann equation. Okay? And therefore, you can now write your Lindblad master equation in a most well-known form. That is that now no hat means I, this comes to the other side with a minus, so this will be H plus what we call the lamp shift Hamiltonian, rho of t, plus sum over k and L and omega of the pi or the gamma, no? It should be the gamma, k L omega is, first we called k, I don't want to break the notation just at the end, L, first L, L of omega rho of t is k of dagger of omega minus 1/2 rho of t is k dagger of omega is L of omega. Okay, this, as I say, the same equation as before, but this form is what is usually called the Limblad master equation. Okay, or the Goranov, I don't know the names. And this one is pretty positive and so on. Okay, and as I say, this term we just can add it to our Hamiltonian, and if we can forget about it, that is what happens in most cases, that they just switch. For one qubit you can very easily see it can only move the eigenvalues, but it doesn't make any other change. Okay, and you can forget about it, but if you have more complicated system, and I will say, okay, prove that you can remove it, you can just include it in your Hamiltonian of your system and forget about it. Okay. Still we can, this is already Limblad master equation, okay? But still we can play with it a little bit. The only thing that is missing, or if you know the Limblad master equation, you would say, okay, Danny, why do you have here this summation is not the usual Limblad master equation we work with, okay? And this is because we can just make something to make our lives easier, to remove this kind of summations, taking advantage that this metric, as we have defined it, is semi-positive definite. And this you can prove just, I have erased the definition, but it just comes from the gamma plus the gamma complex conjugate, so you can prove that it only has positive or zero eigenvalues, okay? And if it is semi-definite positive, you can diagonalize it. And if you diagonalize it, you can just apply here a change of variables. So from this gamma matrix, you go to another matrix, we call capital gamma, that is in this form. Gamma 1 of omega, gamma 2 of omega, gamma n of omega. This is just a unitary change of variables, unitary operator that you multiply, okay? And then you change accordingly these operators, and then you get what is the Limblad master equation in the diagonal form. Li or Li dagger of omega minus 1/2 rho Li dagger of omega Li of omega. And usually you say, okay, there is still something weird, it's not exactly as in books is. Why? Because most of the times they only take into account one frequency, or other way, I can say, okay, this frequency I can just absorb in this index, okay? Just relabel different frequencies at different i's, and increase the number of i's, and I get something like, instead of this, sorry, this is gamma I, gamma I, Li rho, Li dagger, half the anti-commutator of rho Li dagger Li. Yeah, okay. And this is the most canonical way of writing the Limblad master equation. Okay, it is diagonal. You can prove that then it depends on the dimension of your system. You have a definite set of variables. You cannot have, even if you have many different kind of operators. You can reduce it at most at n operators, where n is the dimension of your irreversibility of your system. Okay? Or sometimes you need to work with this case, and then you work with this, and then you diagonalize, and then you go back and forth. Okay, so this is the derivation of the Lindblad master equation, and as I say, this is completely positive and trace preserving. So it generates a transformation, what we call a map, that is a CPT map. And this we will prove, Michalis will prove in other lectures that will come. There is another derivation of this, and we talk about channels and so on and so forth. So what will be missing, that will be the topic of next lecture, is, okay, how do we play with this? How do we calculate, if I give you a density matrix, I give you a Lindblad master equation, how do you calculate the time evolution? Are there steady states? Do they evolve to the same things? Are there more than one steady state? What are the different ways of handling it? Because even if you understood completely the proof, that I hope you did, when the first time you go here and you say, okay, this is a matrix, this is also a matrix, how do I work with it? Okay, it's not the usual equations we are used to work with. Then in the next lecture, I will explain what is the Fock-Liouville space and how do you transform this into a matrix differential equation, and what are the tools to play with it. Okay? So, any questions? Okay, that's it. Thank you very much.